Our speaker for today is Dr. Lauren Zarzar. She's a professor at Penn State with appointments in the Department of Chemistry and the Department of Material Science and Engineering. Prior to Penn State, Professor Zarzar earned a BA in chemistry and a BS in economics from the University of Pennsylvania, a PhD in chemistry from Harvard, and completed a postdoc at MIT. Some of her recognitions include the Packard Fellowship for Science and Engineering, Sloan Research Fellowship, and Camille Dreyfus Teacher Scholar Award. Dr. Zarzar is also a senior editor of the ACS journal Accounts of Material Research. Her group's research interests include the study of colloidal active matter, laser direct writing of nanomaterials, and microoptics. Thank you so much, Dr. Zarzar, for joining us here today. The stage is all yours now.
Thank you again, Professor Zarzar, for this exciting talk. It was so beautiful to see how the different processes in nature has inspired such interesting research. Without further delay, let me quickly jump into the questions. We have received quite a number of questions on different applications, potential applications of these droplets and their interactions. So could you please share your thoughts on what are the potential industrial applications or possible applications as nanomotors or in drug delivery?
Mm-hmm. Yes, so as you actually just mentioned, nanomotors and micromotors have been proposed, for example, for active cargo delivery, potentially for sort of therapeutics. Probably not these droplets. I don't think these droplets would hold up very well in the body for that particular purpose, but you could imagine a solid particle, this, for instance, driven by a reaction, or a lipid nanoparticle that can be motile and maybe shuttle a drug or some other therapeutic to a specific place in the body. There have been some studies looking at how active droplets, for instance, could maybe at a solid surface, you could imagine for surface cleaning or for collecting pollutants. We've done some work on droplet optics. So the Janus droplets, for example, if you can position them in different places, you can orient them. We also have mechanisms to change the structure of the Janus droplet, so the curvature of the interface between the two oils, that can be modified. And you can use the droplets as a lens. So it could be a tunable or responsive optical system as well. Those are just a few examples. I will say these are very fundamental studies. And some of the things that we're learning just in general about how emulsions behave under non-equilibrium conditions at a fundamental level can have implications for applications and use of emulsions that doesn't necessarily have any tie to their active behavior. But things like partitioning, solubilization kinetics, mechanisms, all of those are important for just understanding how emulsion droplets work. And emulsion droplets are used in so many commercial applications, from paints and coatings to foods and personal care product formulations. They're all made with emulsion. So the more that we can understand about non-equilibrium droplets and emulsions, the better.
Thank you, Professor. And we have a few more questions about the role of temperature. So one question is, at what temperature are these experiments carried out?
So all of the experiments I showed, with the exception of the one with the laser where there was a temperature gradient, all of the experiments are carried out at room temperature. So we mostly out of convenience. And then for the situation where we had the temperature gradient, we didn't directly measure the temperature with the laser, but we did apply thermal gradients in another manner laterally, and with only a few degree difference over many, many millimeters, we could generate directed motion and organization of the droplets.
And there is a related question. So, do you think that there is a role for this temperature in the organization of these droplets?
So when we're not applying any sort of temperature gradient, I don't think that temperature is playing too big of a role. We do have, I mean, these droplets are all in a dish where there is a top surface most of the time that's exposed to air. So you can get background convective flows just from having that set up, which you could, tie back to thermal gradients and buoyancy, et cetera. So you have these background convective flows, but they're weak compared to the chemotactic interactions that you're generating between the droplets. So the strength of the droplet interactions with each other is stronger than the background convective flows that you might get from, say, a vertical temperature gradient.
All right. So you were talking about like all the possibilities to control or tune the self-organization of the droplets. So is it possible to control the movement of these droplets?
Control the movement.
Movement and its kinetics?
So the speed of the droplets, their motion can be controlled through a number of parameters. One is their chemistry. Two is the surfactant concentration. So within a range, if you increase the surfactant concentration, you're increasing the solubilization kinetics, you can increase the speed within a range. There's a limit to that. You can also use temperature. So for the Janus droplets, when we did more controlled experiments with temperature, we haven't done this with the single motion droplets, but for the Janus droplets, you could increase the temperature and increase their speed again within a limit, which could be, again, just be due to faster solubilization kinetics. You're basically expending your fuel faster, you're driving everything faster, and that makes the droplets move faster. But there's a limit to all of this. You cannot simply just keep increasing the temperature and expect things to be increasing in speed. But the Janus droplets, we've had those move and up to 200, 250 micrometers per second, so they can get quite fast.
All right. Yeah, as we are running out of time, I would request you to share your final remarks and thoughts before we close the session.
Well, final remarks. Well, thank you, of course, for having me here. Really enjoyed being able to share with you some of this work. If anybody has any follow-up questions that we did not get to, please feel free to send me an email. I didn't put my email on this slide, but you can easily find it by Googling me. And also, as was mentioned at the beginning, I'm an editor for Accounts of Materials Research. So I would love to have contributions from those of you in the audience. If you'd like to learn more about that, please don't hesitate to reach out to me. So thank you very much.
Thank you so much, Reshmi and Jinsi, and Dr. Zarzar for moderating this session of question and answer and for this wonderful question and answer session.